You've probably heard it a million times, right? Spider silk is stronger than steel, tougher than Kevlar. But then you walk right through a spider web and barely even feel it. So what gives? How can both of those things be true? Well, in this explainer, we're going to unravel the incredible science behind how a tiny little spider creates one of the most legendary materials on Earth.
Okay, let's dive right into this paradox, because it's a big one. We're told spider silk is this incredible super material, but our own experience tells us something different. I mean, we've all had that moment, right? Walking through a web, breaking it without even thinking about it. It feels delicate, almost flimsy. So what is the real story here?
And that really is the heart of the matter. It's the question that brings us here today. How can a spider web possibly be stronger than steel if we can destroy it so easily? Is that whole claim just, a myth? Or are we missing a crucial piece of the puzzle? Let's find out.
Okay, so here's the secret. The whole thing hinges on what we actually mean by strength. See, it's not just one thing. Think about it like this. You've got tensile strength. That's how much you can pull on something before it snaps, kind of like a tug-of-war. But then you've got shear strength. That's how easy it is to slice through something. When you walk through a web, you're not really pulling it apart, you're slicing right through it. And that famous stronger than steel comparison? Yep, that is all about tensile strength.
And this isn't just some vague idea. We've got the numbers to prove it. Take a look at this. We're talking ultimate tensile strength here. Your average 836 steel, it clocks in around 400, maybe 500 megapascals. But spider dragline silk? Whoa, we're talking 1,500. That's not just a little bit stronger. Pound for pound, or I guess thread for thread, it's literally 3 times stronger than steel when you try to pull it apart. The only reason a web feels so weak is because those individual threads are just unbelievably, microscopically thin.
All right, so the strength is legit. Mystery solved on that front. But that just opens up a whole new can of worms, doesn't it? How on earth does a spider make this stuff? To really get a grip on the how, we've got to start with the what. Let's zoom way, way in and see what the stuff is actually made of.
Okay, so the main ingredient, the fundamental building block of all spider silk, is a special kind of protein called a spidroin. Yeah, spidroin. You can just think of them as these super long repeating chains, kind of like a string of beads. The beads themselves are amino acids. And these spidroins, they're the raw goo that the spider's going to turn into his superfiber. Now, you might be thinking the secret here is some really rare exotic chemical, right? Something super special, but it's the complete opposite. Get this, the main structural silk, the dragline silk, is almost 60% made of just 2 of the most basic common amino acids you can find, glycine and alanine. That's it. And that right there is the absolute key to this whole thing. The magic isn't in the ingredients. It's not some secret recipe. It's all in how the spider puts them together. It's a masterpiece of biological engineering, taking these super simple building blocks and turning them into something extraordinary.
So, how about a tour of the factory floor? Let's go deep inside the spider's abdomen to see one of the coolest manufacturing processes in all of nature. We're about to see how it turns a liquid protein soup into a solid, super strong thread. Okay, so check this out. A spider's abdomen isn't just some simple tank holding silk. No way. It's more like a high-tech factory with a bunch of different production lines. You've got all these different glands, the major ampullonate, the flagelliform, the aciniform, and each one is a specialized little factory pumping out a different kind of silk with totally different properties. So, one of the first secrets to this whole liquid-to-solid magic trick is some really clever chemistry. As that protein soup travels down this long tube, the environment gets more and more acidic. The pH actually drops. And that change in acidity is like flipping a switch. It's a critical trigger that tells those proteins to start linking up and kicking off the whole solidification process.
Let's walk through this assembly line step by step. First, you've got the liquid protein dope just waiting. Then, bam! Chemical triggers like that pH drop get the party started. Next, that liquid gets squeezed through this super narrow duct, which physically stretches out the proteins and forces them to line up perfectly. And for the final step, water is sucked out, and that's what locks it all into place, a solid, stable fiber. It's basically a tiny, biological 3D printer.
But wait, there's more. The spider's genius doesn't stop at making just one kind of super material. Oh no. It's got a whole toolkit, a whole utility belt of different silks, each one perfectly engineered for a very specific job.
I mean, just look at this toolkit. You've got the dragline silk, that's the stronger than steel stuff we've been talking about, perfect for the main frame of the web and for lifelines. But then you've got this other stuff, viscid silk, which is super stretchy and sticky for capturing prey, aciniform silk, which is tough as nails for wrapping up that prey, and even cylindrical silk for making a soft protective cocoon for its eggs. It's incredible. Each one is a totally different material coming from a different gland inside that same spider.
So you're probably thinking what I'm thinking, right? If this stuff is so amazing, why isn't everything made out of it? Why don't we have spider silk bulletproof vests or bridge cables or, well, anything? Why can't we just copy what the spider does?
Well, it turns out the biggest problem is the spiders themselves. You see, unlike nice, chill silkworms, spiders are, to put it mildly, not team players. They're territorial and they're cannibals. So if you try to set up a spider farm and put a bunch of them together, you don't get a silk factory. You get a tiny eight-legged gladiator pit. They just eat each other. End of story.
This little cannibalism problem has forced scientists to get really creative, and I mean really creative. As one person on Reddit pointed out, and it's true, scientists have gone to some pretty wild lengths. We're talking about genetically engineering goats to produce spider silk proteins in their milk. I'm not kidding. That's right, spider goats. If that doesn't show you how badly we want to figure this out, I don't know what will.
Okay, so we've looked at the chemistry, the biology, the crazy engineering, so what's the final verdict on spider silk? Let's pull all these threads together one last time.
It really all boils down to this. You start with a recipe of super simple, everyday proteins. Then you run them through this unbelievably sophisticated, tiny little factory that uses precise chemical and physical triggers. And what comes out the other end isn't just one material, it's an entire toolkit of high-performance fibers. It's just the ultimate example of lightweight, hyper-efficient, and multi-purpose engineering, all cooked up by nature.
And you know, spider silk is such a great reminder that some of the most mind-blowing engineering on the planet isn't happening in some high-tech lab. It's happening all around us, in the natural world. It really makes you wonder, doesn't it? What other amazing secrets are just hiding out there in plain sight, waiting for us to unravel them?